Hello, the topic of our discussion in this video tutorial is the Cauchy Criterion. Let me first give you what is the definition of a Cauchy sequence. A sequence, AN, is called Cauchy if and only if for all epsilon strictly positive, we can find or there exists n a natural number so that the difference between an term and the am term less than epsilon when n comma m they are greater than or is equal to n. Or in other words, a sequence is Cauchy if we can find a natural number n when the n and m is bigger than or is equal to that capital N, the term of the sequence get really close. Or in other, an minus am is less than epsilon. Now, this definition look very similar to the convergent sequence, but there is a one really little subtle difference between what is a Cauchy sequence and what is a convergent sequence. Let me first write down the definition of the convergent sequence, and then I will show you what is the main difference between these two definitions. So here is the definition of a convergent sequence. And as you can say, the main difference between a Cauchy sequence and convergent sequence is if a sequence is convergent, then the term of the sequence get close to some fixed number L as the indices is bigger than or is equal to some natural number N. But here we are saying the term of the sequence are really close when n and m, when these indices are greater than or is equal to some natural number n. So this is the major and subtle difference between the Cauchy sequence and the convergent sequence, that we take two terms in a Cauchy sequence, and in the convergent sequence we only need to take one term, and also we need to find a real number L. Next, I will show you one example of a Cauchy sequence. So an is equal to 1 over n. This is a Cauchy sequence. And we can also prove that this is a Cauchy sequence by using the definition of the Cauchy sequence. To prove this, what we need to do is for all epsilon positive, we need to find capital N. So this is what we will be looking for, so that an and minus am, this distance is less than epsilon. So what we will do, we will first try to calculate what is an and am. This is a simply 1 over n minus 1 over m and the absolute value of that. If I make the same denominator and simplify, this will be m minus n and divide by n time m. I put the absolute values of the in the denominator and also in the denominator. Since n and m, they are both natural numbers, so they are positive. So I don't need to put the absolute value around n multiplied by m. Now I'm gonna, without loss of generality, assume m is strictly greater than n. So I can remove the absolute value. So this is m minus n time n. And here I assume without loss of generality, m is strictly greater than or is equal to that little n. Now if I drop the n, so I will have less than or equal to inequality because n is a positive number. So this is a m time n, and this is simply 1 over n. Now, if I use the Archimedean property, the second part of the Archimedean property, I can make this less than is equal to epsilon when n is bigger than or is equal to capital N. And that capital N is coming from the Archimedean property. So the Archimedean property say that for every epsilon positive for every real number, you can find the capital N so that 1 over n is less than is equal to that real number when n is greater than or is equal to n. So this n is basically what we need to find. So we found it here. Now we will write down the formal proof, since this is a sort of a scratch work. So for a formal proof, what we say, for epsilon greater than or equal to 0, we take capital N such that 1 over n is less than epsilon when n is bigger than or is equal to that capital N, and this is possible by Archimedean property. So that if I calculate the difference between now an and am, so now I can repeat my all the calculation which I did here. This simply will be less than is equal to 1 over n, and I know that 1 over n is less than epsilon when n is bigger than or is equal to capital N. So this implies also an minus am, this is less than epsilon. Since m is also bigger than or is equal to n, this we assume. So if n is bigger than or is equal to n, so it means m automatically will be also bigger than or is equal to n. And this is the definition of a Cauchy sequence. So this implies, by definition, the sequence an is a Cauchy. So this completes the proof of this example that the sequence an, which is equal to 1 over n, is a Cauchy sequence. Next, we will prove this important result, which says that if a sequence is convergent, it must be a Cauchy. As usual, first I will write down what is given and what I need to prove. So given statement is a sequence is given an, which is a convergent. So I can assume that sequence is, let's suppose, converges to L. What I want to show, or what we need to prove, is that sequence an is Cauchy. And we will use the definition to prove that the sequence is Cauchy. First, I will take what is given. So since the sequence is convergent, so I will use the definition for epsilon positive. There will exist, so I can find basically a number n, which is belong to the set of natural number, so that an minus L is less than epsilon divided by 2. Instead of taking epsilon, I will take epsilon divided by 2. So an minus L is less than epsilon when n is bigger than or equal to that capital number n. So this is, we have given. So this inequality is given when n, the little n, is bigger than or is equal to capital N. The difference between an minus L is less than epsilon half. To prove that the sequence is a Cauchy, so what we need to do is, for all epsilon positive, we need to find, we take this time, we will take n, capital N. I'm going to take the same capital N which I took before, which I find before. So this capital N, and we need to show, when n comma m, if I pick two term n comma m, when they are bigger than or capital N, I need to show is this basically, the difference between an and am is less than epsilon. This is what I need to show. So let's begin calculating what is a an minus am. This is nothing, but this is also is equal to an minus L plus L minus am. I add one L and I also subtract one L. And now I will use the triangle inequality on these two terms. So this is a less than is equal to an minus L plus L minus am. And this will be is equal to an minus L. So since I have absolute value, I can flip these term. So this will be am minus L. So now if I choose n is bigger than capital N, so if I choose n is bigger than or is equal to capital N, then this inequality will hold. So an minus L will be less than or is equal to epsilon half, which will come from this inequality. Because if n is a bigger than is equal to this, then difference between an minus L is less than half. Now, if I also choose m is bigger than or is equal to capital N, and I replace this n, because if this is a true for n is bigger than is equal to m, so if I replace n by m, so this inequality will also hold. So this implies this is also less than 1/2. What basically we prove that when n comma m, they are both greater than or is equal to n, the difference between an and am is less than epsilon. And this shows that this sequence is the sequence an is Cauchy. So this proves our theorem. Next, I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, we will prove another important result, which says that every Cauchy sequence is a bounded sequence. So this is our theorem number 2. Let's begin the proof. So first, I will write down what is a given, and then I will also write down what we need to prove. So given. So this time given, a sequence is a given, and this sequence is Cauchy. And what we want to show or what we want to prove, the sequence an is bounded. Let me give you a recall. What does mean by a sequence is bounded? A sequence is bounded if we can find a positive real number m, so that each term of the sequence is less, absolute value of the each term of the sequence is less than that real number m, and this is true for all n. So again, we will start from what is given. So the given is the an is a Cauchy sequence. So this time I'm gonna take epsilon is equal to 1. And since for each epsilon, we can find n. So therefore epsilon is equal to 1. We have or we can find capital N, which is a belong to the set of natural number, so that the difference between the term an and am, this is now less than 1 when n and m, they are bigger than or equal to capital N. And this also implies, since this inequality is true for all n and all m, which is bigger than or is equal to capital N, it means this inequality is true for when m is equal to n. So if I plug the value of m is equal to capital N, so I get an minus a capital N. This will be also less than 1 when now n is bigger than or is equal to capital N. So I fix the m and I choose the value of the m is equal to that capital number n. Now I need to compute basically a n term, and I need to show that this term is bounded. So what I will do some manipulation. I'm going to calculate an, and I'm adding capital N, subtracting and adding a capital N term. And I will use the triangle inequality to have an minus a capital N plus a capital N. And I know this is less than 1 when the little n is bigger than that capital N. So this shows that when the little n, this little n is bigger than that capital N, all the term of the sequence are bounded. And we know that if the n is less than or is equal to capital N, there are finite number of an terms. Since all the finite set of real number are bounded, so we can bound each all of those terms. So now I'm going to choose m. So if I choose my m as a1, a2 up to a capital N minus 1 and 1 plus a capital N, then what we will have, this will show that an will be always less than is equal to the capital M, because M is the maximum of all the term vary from 1 to capital N minus 1, so which is here. And when n is bigger than or is equal to capital N, all the term are less than this, so this is the maximum. So therefore, this is a true for all values of n, the values which are less than n and which are bigger than or is equal to capital N. And this also shows that the sequence an is bounded. And this completes the proof of this theorem. Next, we will state and prove the main result of this lecture, which is Cauchy criteria. The Cauchy criteria say that a sequence is convergent if and only if it is a Cauchy sequence. So this theorem has two directions. The forward direction is if the sequence is convergent, then it is a Cauchy. And if the sequence is Cauchy, then it is a convergent sequence. So let me write down the proof. The forward direction is if the sequence an is convergent, this implies the sequence an is Cauchy, and we already proved this result in our first theorem. So look at the theorem number 1. So what is the reverse direction? So the reverse direction is if the sequence an, for example, is Cauchy, so this is given. In that case, we need to prove the sequence an is convergent. So this is what we need to show. So let's again start from what is given. So since the sequence an is Cauchy, and by theorem number 2, this sequence will be also bounded. We just proved that every Cauchy sequence is bounded. So this is a by theorem number 2 of this lecture. So if a sequence is bounded, we can use the Bolzano-Weierstrass theorem. So by Bolzano-Weierstrass theorem, we can find or there exists a subsequence a n of k, and that subsequence must be a convergent sequence. So we can assume that there exists a subsequence and that sequence is converges to L. What does mean by a convergent sequence? It means for all epsilon, this time I'm gonna take epsilon half positive, there exist, I'm gonna choose n1, which is a natural number, so that the difference between a n's of k minus L is less than epsilon half when k is bigger than or is equal to n1. So this also implies that this inequality an of k minus L is less than or is equal to f for every value of k which is a bigger than n1. So I'm gonna fix now k. So I'm gonna choose k is equal to n1. So this inequality will hold for a fixed values of k which is a bigger than or is equal to n1. We have also given that the sequence, the given sequence is Cauchy. So this is also given. So we will use the definition of the Cauchy sequence. So by definition, epsilon positive, we can find there will exist, this time I'm choosing n2, so that the difference between an and am is less than epsilon divided by 2. So let's choose epsilon divided by 2. When n comma m, they both bigger than or equal to n2. So now we have two important inequality, this one and this one. So the next thing is I'm going to take, so let's take, choose capital N, which will be the max of capital N1 and capital N2. So if I choose N is bigger than or is equal to that capital N, so it means N is also bigger than is equal to N1 and also N is bigger than is equal to N2. And I will compute this term an minus L, and I will show that if the little n is bigger than or is equal to this capital N, this term an minus L, this is a less than epsilon. So I'm gonna do some manipulation. If an, I'm gonna add an and 1, n's of 1, and if I subtract, I have to also add, and then we have minus L. I will use the triangular inequality to get this term and 1, and here an of 1 minus L. So since n is bigger than or equal to capital N, so this implies n is also bigger than or equal to n2. So if n is bigger than or is equal to n2, this will also implies n's of n1 will be bigger than or is equal to n2. Because this sequence n's of n1 is an increasing sequence, so we can basically make that bigger than is equal to n2, because n2 is the sequence of n2 is just a natural number. So and capital N is basically the maximum of n1 and n2. So now what we have this script and this script, they are both bigger than or is equal to n2, because n1 is also bigger than is equal to n2, and n's of n1 is also bigger than n2. It means this inequality hold. So this term is less than epsilon divided by 2. And this term is already basically have this inequality. It is a true for a n's of n1. So this is a epsilon divided by 2. So that lead us to this term is less than epsilon. So let me write one more time what we show. We showed the difference between an and L is less than epsilon when n is bigger than or is equal to that capital N. This implies the sequence an is convergent and it converges to L. So this completes the proof of our theorem. Next, I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.